to this EAGE lecture. My name is Dilma Klüver. I'm a research geophysicist with PGS, and I'm going to make with you the transition from discrete shot records to continuous wave fields. I'm going to present a novel marine seismic acquisition processing method and illustrate it with real data examples. I will have an introduction, really summarizing key steps of the novel method we're going to introduce. I will then introduce the way we build a source wave field, which is specific to this method, especially how we approach the properties of white noise using existing airgun equipments. And then in the third part, I will take you through the field data case study, and finally I will summarize. So the proposed method is a seismic method that utilizes continuous source and receiver wave fields. On the receiving side, we are continuously recording the data from an entire saline at once and treat this as one record. This is very different to what conventionally is done, where the record is split up in about 10-second long chunks of data. On the source side, we are going to generate a source wave field which is continuous as well, and I'm going to describe more details on this later on in this lecture. Special emphasis in this lecture is how we generate the source wave field with existing airgun equipment, and this is a project which has been funded by the Research Council of Norway, Equinor, and PGS. On this slide, you see a summary of key steps in this method. In the left-hand lower corner, you see a blue strip, vertical strip of data that is representing the data we record in the field. The lateral width of this strip is the streamer length, so this is typically about 8 kilometers wide. The time axis is different from conventional seismic. This is several hours long. It is the time it takes to record one saline. As a first key step, we shift these data laterally in space, that we can generate data as if we had stationary receivers in the field. Then you end up with the diagonal strip of data, which is shown immediately to the right. And when we then consider one of those stationary receivers, this is a trace I highlighted in yellow, then you will see that at one point in time it starts recording data, and at one point it ends recording data. It starts recording data when the first channel in the streamer is passing through the stationary receiver position, and it ends recording data when the last channel is passing through that receiver trace position. The temporal length of these receiver traces depends both on cable length and vessel speed. So if we have an 8-kilometer long cable and 2 meters per second vessel speed, then this trace would be 4,000 seconds long. The red stippled line is the source position relative to the streamer. And the source is moving with the seismic vessel. And if you consider a stationary receiver, the source is moving away from the stationary receiver position as a function of time. And all energy emitted by the source up to the end of the receiver trace can potentially contribute to that receiver trace. And as you can see, the source wave field then has a temporal and spatial extent, so this is a multidimensional operator. On the top, you see a stationary receiver trace, which is, this is a synthetic trace we've modeled on a 3D Earth model. The amplitudes are typically highest in the beginning and then decay towards the end of the receiver trace. This is just reflecting the fact that the source is moving away from a stationary receiver. And later on in the presentation, I'm going to explain an iterative source deconvolution scheme. That scheme we use to extract the response of the Earth from this single receiver trace. And you see the extracted Earth response at the bottom right. You see 6 common receiver gathers. We get 1 gather for every string of airguns we have in the field in 6 different crossline positions. And you see lots of diffracted events here which systematically move as we go from one source to the next. This is just reflecting that this is a true 3D deconvolution we are performing. The sources in this case have been placed 200 meters beside each other in the crossline direction, so we have a total source spread width of 1 kilometer. But I'm coming back to this iterative scheme later on in the presentation. So now how do we generate the source wave field we need for this method? The ideal source wave field would be generated by a device which continuously emitted band-limited white noise. And somehow we need to find a way to approach the properties of white noise with air guns. And that is what I'm going to describe in the following slides. So you see here the 6 strings of air guns a seismic vessel typically tows. These are the yellow vertical bars. Each string we equip with 6 air guns of 3 different volumes. And you see that the arrangement of these volumes is different on each string. And as we cycle through all these air guns, we generate a high degree of coding both in the inline and crossline direction. So this is a highly coded wave field we are going to deconvolve later on from the data. You further see that there are 7 near-field hydrophones indicated by small red boxes on each string. We are only ever triggering 1 single air gun at a time. So when we solve for notional source signatures later on, we have a highly overdetermined system compared to the usually just about determined system solved in conventional seismic acquisition. So we can actually solve for more than just the notionals, but also for bubble-wise features and so forth. Here you see the notionals we have determined in a field test for one of the air guns in the bottom figure. There were more than 600 activations of this single air guns, and you see small scale variations from one triggering to the next. And all these small scale variations are going to be part of the source wave field we're building before we deconvolve it from the seismic data. So we're going to account for all those small scale variations in the deconvolution process. The air guns are triggered very dense in time, typically about 250 milliseconds apart with a randomized triggering interval. On this slide, you see the field test we performed with this source setup. You see 6 common receiver gathers, 1 gather for each string of air guns we had in the water. This is a very deep water setting offshore the Cape Verde Islands. The water bottom is coming in at about 7.5 seconds. On the most right-hand side, you see the difference between source 1 and source 6, which contains quite a lot of energy. This is energy which has been emitted from the source with a large angle sideways. And this is just reflecting that this is a true 3D deconvolution we are performing. We are getting the Earth response in a true 3D sense. So it's not that we generate 6 receiver gathers which are the same, even though the sources are fairly close together in this field test, but they really pick up the 3D emission of the source wave field. We only trigger 1 air gun at a time with this source wave field. That means that we emit a lot less energy. And if we integrate this energy over a typical record length of 10 seconds and compare it to a standard size air gun array, which is the figure shown at the top, 4130 cubic inch array, then we see that we have lowered the sound exposure level quite significantly. At the bottom, you see the energy we emit when we trigger individual air guns, and the color scheme shows that we have reduced the SEL quite significantly. The horizontal axis is distance from the source, and the vertical axis is vertical distance from the source, and this has been simulated over a homogeneous half space filled with water. I'm now taking you through the field data case study. In summer 2014, PGS acquired a field test offshore the Faroe Islands, a little bit southeast to the islands, with a source setup as previously described. And we acquired this line previously with a time and depth distributed source. The line has a length of about 60 kilometers, and we are going to use this previous acquisition as a baseline to compare against. In terms of acquisition setup, the time and depth distributed source had a 25-meter nominal shot point spacing. The source is split into 2 parts, which are triggered with a ±1 second randomization between the individual subsources. The air guns are distributed over 2 different depths, so each subsource has a different depth. They are separated later on by deblending in processing and then combined again to fill the source ghost notch. The source is very big. It has in total more than 7,000 cubic inch volume. In the proposed method, we only trigger 1 air gun at a time. In this survey, we triggered about every second on average. This was a limitation in the gun controller at the time we acquired the survey. So there is approximately 2.5 meter spacing between consecutive firings. The entire source consisted of 1,250 cubic inch air guns, and they were distributed over 3 different depths. We need 3 different depths to get complementary bubble pulses to get a stable deconvolution operator later on. So here you see the emitted vertical wave field. In red, you see the reference source wave field from the time and depth distributed source. You see 2 spikes each, indicating the individual subsources, which have a randomized triggering against each other. And you see that this is very large peak sound pressure level compared to the individual 150 cubic inch air guns, which are shown in blue. So those are triggered on average every 1 second, but with randomized time intervals in between them. So we get a significant reduction of the sound pressure level, in this case about a factor 30 with the proposed method. In terms of spatial sampling, if we have 25-meter short point spacing, we get 25-meter trace spacing in common receiver gathers in the conventional case, meaning that with 12.5-meter channel spacing in the streamer, we have asymmetric spatial sampling in shot and receiver, and there will obviously be aliased energy in shot and receiver gathers as well. In the proposed method, when we process at 4 milliseconds, we solve for 6.25-meter trace spacing in common receiver gathers in processing, then anti-alias protect and decimate to 12.5-meter trace spacing to get symmetric spatial sampling in shot and receiver gathers. So the receiver gathers are fully anti-alias protected in this case. Here you see the recorded data after receiver motion correction. On the left-hand side, you see the first 20 seconds being recorded. This looks more like a normal length bracket, but you immediately see the dense triggering of the individual air guns. If you look at the first 100 seconds, you can already see how we move the data in space from left to right. There is an empty triangle appearing on the lower left corner and at the upper right corner. If you look at the first 7,000 seconds, this looks pretty much like the cartoon I've shown in the very beginning. And the actual length of the data is about 3 times as long as what we are showing here. And one trace in this data matrix is one stationary common receiver trace, where we are going to deconvolve the source wave field from. The source wave field then looks like this in FK. It is pretty much spatially wide within the signal cone. There are some undulations in frequency. This is due to the fact that the 3 different bubble pulses are not fully complementary to each other, but these are not very deep notches, so this is a very stable wave field to be deconvolved from the receiver trace. In the following slides, I'm then going to explain how we are going to deconvolve the source wave field from a single receiver trace. On this slide, you see the recorded receiver trace on the right-hand figure. The amplitudes are largest in the beginning and then decay as time increases. This is reflecting the fact that the source is moving away from the stationary receiver position. When we deconvolve the source wave field, we don't have any source emission angle information in a single receiver trace. So what we do is we spread the energy in the common receiver trace over all possible source emission angles, then make a multidimensional deconvolution of the source wave field to end with the deconvolution result, which is shown in the center of these 3 figures. All the energy focuses in the correct spatial position, since we have placed all energy in all possible source emission angles, but obviously we generate some noise in this process since we spread energy also into incorrect source emission angles. So we are now going to extract coherent energy from this deconvolution result and put it into the extracted signal bucket, which is shown on the left. Then we model the contribution of this extracted signal to the receiver trace. The modeled receiver trace is shown in red on the right-hand side, and subtracted from the input receiver trace. And that is the receiver trace which is shown in green, the residual receiver trace. We then deconvolve the source wave field from this residual receiver trace again to get the deconvolution result shown in the center. As you can see, all the energy we have extracted is not appearing in the deconvolution result since it's no longer present in the residual receiver trace. And all the noise associated with it is absent as well. So we get a cleaner deconvolution result. And now we are able to extract further signals from this deconvolution result and model again the contribution to the receiver trace, and we continue these iterations until we are no longer able to extract any energy from the common receiver trace. we end up with a very small residual receiver trace shown in green. We deconvolve the source wave field from this residual receiver trace and then add it back to the extracted signal in order not to lose anything we have recorded in the field. And the final result then is shown on the left. This is a lot cleaner than the initial deconvolution result, which is shown in the center and contains all the signal in the correct place. We do this for all receiver traces we acquire along the line, and this is showing an example receiver gather in the left for the proposed methodology. On the right, we have built a common receiver gather from the conventional data that has 25-meter trace spacing and obviously contains a lot of spatial aliasing. There's no spatial aliasing in the receiver gather from the proposed method. Overall, they have a very similar signal-to-noise ratio, even though we have emitted about a factor 6 less energy with the proposed method. We then took the data through an imaging workflow, and I'm going to show here 2 time-migrated images. The challenge in this area offshore the Faroe Islands is to penetrate a basalt layer deep down in the earth. You see this basalt layer here starting at 2.8 seconds on the left-hand side and ending at about 1.5 seconds on the right-hand side. Typically, one uses very big sources emitting a lot of energy at once to penetrate this basalt layer. But even though we emit a lot less energy and only trigger a single 150 cubic inch air gun at a time, we get about the same penetration through this basalt layer. I'm now going to show the shallow resolution in this rectangle I'm highlighting here. Both of them are fairly high resolution data sets, but we have 12.5 meter inline trace spacing, shot point spacing with the proposed method compared to the 25 meter shot point spacing in the time and depth distributed source. And that shows when in the resolution we get on the fault planes in this case, which are better resolved. So now I'm going to summarize what I've presented to you today. We have demonstrated a novel acquisition and processing method and shown some real data examples. Special emphasis in this presentation was given on how we generate a source wave field which approaches the properties of white noise. And we do this by densely triggering individual air guns with randomized time intervals. The continuous wave fields on both the source and receiver side allow much denser trace spacing in common receiver gathers, and those can be fully anti-alias protected. And they also allow potentially larger imaging depth since there's no listening time, and we can deconvolve the source wave field for any time range we like. With typically 6 strings of air guns on a seismic vessel, we can deconvolve the source into 6 different crossline source positions. This allows denser crossline CP spacing and/or increased efficiency. There is an environmental benefit with this method since the energy is spread out in time, so we can significantly reduce the peak sound pressure level and also reduce the sound exposure level. And despite the fact that we emit a lot less energy from this smaller source, we definitely get the same penetration when we compare to a larger source in this 2D field data example. With that, I would like to thank you for your attention. And if you like this presentation, please have a look at the EAG YouTube channel for similar lectures.